Here we have a crank that is used to drive this piston. The angular velocity of the crankshaft is the rate of change of the angle theta. So here's angle theta, so d theta dt is the angular velocity, omega. So the piston moves horizontally with velocity vp and acceleration ap. R is the length of the crank and L is the length of the connecting rod. The crank pin performs circular motion with a velocity of vc and centripetal acceleration omega squared r. The acceleration ap of the piston varies with theta and is related by ap equals omega squared r into cos theta plus r cos 2 theta over L. Now you probably know from circular motion that if a point moves at constant speed in a circle, then its acceleration is given by omega squared r. Omega will be a constant if the point is moving at constant speed. The angular velocity is omega. Omega squared r times cos theta would actually give us the horizontal component of AC. AC is directed towards the center of the circle, so that would give us this, one of the terms of the acceleration of the piston. But then we have a second term which I won't go into. Anyway, we just take this formula as a given. I might derive it in another video. We want the maximum and minimum values of the acceleration AP when r is 150 millimeters and L is 375 millimeters. So theta is the independent variable here. I suppose it appears that omega is taken as a constant. That's the angular velocity of the crankshaft, so this is turning at a constant rate. So to find the value of theta that maximizes or minimizes the acceleration, we have to differentiate A with respect to theta and set the derivative equal to 0 and solve. So omega, r and L are constants, so we look at cos theta, differentiate it with respect to theta, but the derivative of the cos function is minus sine. And as for this function cos 2 theta, we use the chain rule, differentiate the cos function to get minus sine 2 theta, then multiply by the derivative of the angle. The derivative of 2 theta with respect to theta is 2. So we set the derivative equal to 0 and solve. So since omega and r are constants, we can ignore that. We just set what's inside the bracket equal to 0. And now we have to solve this trigonometric equation for theta. We can write sine 2 theta as 2 sine theta cos theta. If we do that, we now see that all our angles are in terms of theta. Initially we had one angle is theta and the other angle is 2 theta. At least all the angles are the same here now. We can factorize sine of theta out of this equation. So we have this product equal to 0. So we set each factor in a turn equal to 0. We set sine theta equal to 0, and then we can set what's inside the bracket equal to 0. From the other equation we get cos theta equals minus L over 4r, and we plug in the given values for r and L. Let's consider the case where sine of theta is 0. Well, there's only two values of theta that will solve that. Theta equals 0 or theta equals pi radians. They're the only values of theta in the range from 0 to 2 pi radians. That's a full revolution of the crank pin. Let's start with theta equals 0. Well, let's go back to the formula for the acceleration. If theta is 0, then the cos of 0 is 1. Well, the cos of 2 times 0 is also 1, of course. So we can plug in for cos theta and cos 2 theta. So we've 1 in for cos theta and 1 in for cos 2 theta. And we plug in our values for r and L. That's 150 and 375. So 150 divided by 375 is 2/5. Now the acceleration is given in terms of omega squared r actually. That's the centripetal acceleration of the crank pin. Omega squared r is AC. For constant circular motion, this vector AC is always pointing towards the center of the circle, and its magnitude is constant. Its direction keeps varying, of course, as the crank pin goes around the circle, but its magnitude is constant omega squared r. Now the other value for sine theta is sine for the other solution, sine theta equals 0 is theta equals pi. So if we plug that in here, we get the cos of pi. Well, that's actually minus 1. The cos of 2 times pi, well, that's the same as the cos of 0, which is plus 1. So r over L is 2/5, and we get minus 3/5 omega squared r in that case. So we have two stationary points here at θ equals 0 and at θ equals pi. In order to classify them, we need to take the second derivative. So if we go back up here, we have the first derivative. So we need to differentiate this again. The derivative of the sine function is cos. So we're going to get a minus cos θ there. That's what we have there. And then we have to differentiate sine 2θ. The derivative of the sine function is cos, so we get cos 2θ, but then we multiply by 2. So we're going to get minus 4r cos 4θ there by the chain rule. Sorry, minus 4r cos 2θ. So we examine the second derivative at the two values of θ equals 0 and θ equals pi. At θ equals 0, we get the cos of 0 as 1. That's a 1. We have another cos of 0 here, which is another 1. We can take the minus sign out here, and we see that this quantity is negative because omega, r, and L are positive. So that means we have a local maximum at θ equals 0. And the value of it, as we've seen before, is 7/5 omega squared r. Now the other stationary point occurs at θ equals pi. So we plug pi in here. The cos of pi is minus 1. The cos of 2 pi is the same as the cos of 0, which is plus 1. Okay, this should be 4r over L. So r is 150, L is 375. R over L is actually 2/5. 150 divided by 375 is 2/5 times 4 is 8/5. 8/5 minus 1 is plus 3/5. And since omega and r are positive, this quantity is negative. So the second derivative is negative at θ equals 0. So that means that we have a local maximum at, θ equals pi. So now we've dealt with the two stationary points that come from the equation sine θ equals 0. Next we look at the equation cos θ equals minus 5/8. So we want the acceleration that goes with that value of θ. So here's our formula for the acceleration. So we plug minus 5/8 in for cos θ. Now what about cos 2θ? Well, we could just solve this to get θ and then double it and then get cos of 2θ, or we could use this identity. So we'll use this identity for cos 2θ. Plug 5/8 in there, square it. So we get 25 over 64 times 2, that's 50 over 64 minus 1. That's minus 14 over 64, or minus 7 over 32. So we plug that in for cos 2θ. Okay, we have r over L, that's 150 over 375, that's 2/5. Working this out, we get a negative value actually. Now to see what kind of a stationary point this is, we get the second derivative and plug in. So we found that cos θ is minus 5/8, so we plug that in here. Minus 5/8 in for cos θ, and we know that cos 2θ will be minus 7 over 32. So we plug that in here, and r over L is going to be 2/5. Anyway, the whole thing is going to be positive, which means that we have a minimum at the value of θ that gives cos θ equals minus 5/8. We haven't actually worked out θ, but it solves this equation. So here are the values of AP at the stationary points.